Hello everyone, welcome to the 10th webinar in the Joint TranSET webinar series, which will cover a variety of projects related to innovative techniques in detecting, monitoring, and planning for flooding from three quite different perspectives. Today we are having three experts presenting in this webinar. We will have three 15 to 20-minute presentations. First, Dr. Gabriele Villarini will provide a comprehensive overview on the Iowa Flood Center and the projected change in flooding across Iowa. After that, Mr. David Heman will discuss the U.S. Geological Survey stream flow and precipitation-based flood warning and inundation mapping integrated with water alert and water watch tools for selected communities in Missouri. Finally, Dr. Seyon Ham will discuss real-time early detection and monitoring of flooding using low-cost, highly sensitivity ultrasonic sensing of water level. We will save questions until the end of the three presentations for a 15-minute group Q&A. You can type your question anytime throughout the session. Without further ado, I will introduce our first speaker, Dr. Gabriele. Dr. Villarini is a professor in the Civil and Environmental Engineering Department at the University of Iowa. He is also the director of the IIHR Hydroscience and Engineering. Dr. Gabriele, I will turn it over to you now.
During the peak of the flood, and so this is one of those events that really left a strong impression on me, on the community we live in. And from my perspective, I've always been interested ever since in understanding what causes these kind of events, whether they're predictable, and what they're going to look like in the future. And so that gives you a little bit of a sense for where I'm going with today's presentation. But again, rewind to 2008. All we could do was, at the time, was helping sandbagging the river. In 2009, in the 2009 session, the state of Iowa established the Iowa Flood Center. So this is the language from the legislature, and you don't need to read everything. I'm just going to quickly highlight some of the main missions and tasks for the Iowa Flood Center. In particular, you can look at physically based flood frequency estimation, real-time forecasting of floods, floodplain inundation and mapping, improve flood monitoring, share resources and expertise, and development of a workforce. And I think that given the focus of today's webinar, many of the elements that I will be talking about in relation to the detection, the monitoring, fit nicely within that scope. So let me start with the flood monitoring, and I know that I'm going to be followed by an expert at USGS, and so I won't get into too many details. But if you think about it from a data perspective, USGS is the golden standard in terms of monitoring the waterways and archiving, disseminating the data, and they do a fantastic job. Now, as we all know, we all deal with resource constraints, and obviously we can't monitor the waterways everywhere or nearly at as many locations as we would like. And so as part of the Iowa Flood Center initial efforts, we worked on the development of what we call bridge sensors. These bridge sensors are economic alternatives to monitor the waterways. And the way that it works, you can see from here. They are installed on the downstream side of overpasses, in this case, or bridges. There is an ultrasonic sensor in there, emits a pulse, and it gives you the distance between the sensor and the water level. These are cheap devices. They are low maintenance, low to no maintenance, I would say. Many of them have been out in the field for 10 plus years. And you can imagine, if for those who are familiar with Iowa's weather, we have harsh winters with temperature dropping below in the negative, and we had the peaks down to -50. And then we're characterized by hot summers. And these bridge sensors have been working with, as I mentioned, little to no maintenance for a decade plus. There is inside a modem that sends the signal to the cell towers, which then relays to our information system. The advantage of having these economic low maintenance devices is that we can complement the network that has been maintained by the US Geological Survey. In Iowa, we have about 120 sites monitored by the USGS, and they tend to be focused on the bigger communities or in the bigger streams. And here they are identified by these green symbols. The blue symbols are the bridge sensors that have been installed. We have about 250 of them, and they complement nicely the USGS data, providing us with information at smaller location, giving us a more comprehensive view of water levels in the state. As I mentioned, they are robust and they are very resilient. This is just a time series from our information system. You can see how the river responded. The sensor basically got submerged, and when it got submerged, there is no signal again. But as the water started to recede, you can see how they started operating again. And this is not just one site. This is representative of many other locations. I'm going to switch now to the flood mapping side. And one of the elements that I remember vividly in 2008 was that when in the news they were saying the river is going to crest at, say, 35 feet. Okay, what does it mean? How am I going to interpret that piece of information? Where do I know whether I'm supposed to stay, whether I'm supposed to go, whether I need to move stuff out of my basement? And so that hydrologic context was missing. And as I mentioned, all we could do was sandbagging. Now in 2009, we were put to work because of the expertise that we have at IIHR. And we have been developing a flood mapping for the entire state of Iowa. The advantage of having us doing the entire state rather than consultants from, say, out of state is that you're going to get an homogeneous set of maps. You don't worry about stitching together maps from different companies for different localities. And this was a multi-year, multi-million-dollar project that we led together with local partners. And they comprised of 4 parts, from hydrography to hydrology to the hydraulics to the mapping. And now what we have is an online system that provides you with information about flood inundation across the entire state. This is a map for the 500-year flood inundation map. And this is for here's the University of Iowa, here is Iowa City. We have the same available for the entire country. And some of the maps have been going through review by FEMA, the Federal Emergency Management Agency, to be used for premium for policy pricing. In addition to creating flood maps, we also incorporated the FEMA's HAZUS dataset, which tells us about the buildings, as well as gives us vulnerability curves, which allow us to relate water level and water depth, as you can see here, to damage. And here, this is for the city of Cedar Rapids. This is for the stage at 34.5 feet. You can see in the bottom left corner what how many affected buildings there were, and the structural and the content damage. And as you see from this slider, you can toggle it and move it to get the different stage levels and get different sets of impacts. And so this is another way of complementing the flood inundation mapping. Now, this was focused in a sense, kind of like a present and retrospective perspective. We also work on flood forecasting. The reason is, if you look at the National Weather Service, which is the agency in charge of issuing forecast for our country. Within the state of Iowa, they issue forecasts at about 100 sites, and they tend to match the bigger communities. Here, given the mandate that we have, we complement what the National Weather Service does and work closely with them and issue forecasts at over 1,000 locations within the state. We also have a connection with them, and they are able to look at our forecast and use it as an additional way of getting sense for what's going to be coming down. And so we have this forecast. It's issued every 15 minutes for the entire state in real time, and it goes out to a few days. We have different scenarios that we also examine, from a what-if scenario of, say, 2 inches of rain within the next 24 hours to persistence. So what if the rain stopped? To incorporating the rainfall forecast from the National Weather Service. And this just gives you an idea. We have a rainfall product that we use, that we have developed in-house because of the extensive expertise that we have on remote sensing of rainfall. We use this as input to the hydrologic model that we have developed. It's called HLM, Hill Slope Link Model. It's a calibration-free, physically based model that runs operationally for the entire state. Every 15 minutes it gets updated. And it also, in terms of monitoring, we not only look at bridge sensors, but we also have a series of weather stations. In this case, this is a snapshot from a dual tipping bucket rain gauge, soil temperature sensors, and soil moisture probes, a different depth within the ground. And this is what one view of one of the products that we've created. So for the entire state, you have information about the rivers, and you have a potential seasonal outlook for potential flood outlook for community of interest. It tells you what the outlook looks like for the next few days, whether there is a higher or enhanced flood potential, or things are looking okay. And this is for this watershed. As you can see, there is also a hydrologic context to the information that is provided to the communities. Now, in terms of flood information, your products, at least the perspective is that what you do is just as good as the way that it can be digested by the public, as this is not an academic only perspective on it, but we have been tasked by the state to provide flood information for the entire state. And so we've been spending a lot of effort in the realm of hydroinformatics and developing online platforms that provide you access to all this data. The way I like to think of the Iowa Flood Information System, and so if you Google it, you would find it right away, is it's a one-stop shop for all of your hydrometeorological needs. There is no login, there is no password. All you do, you click here on Launch IFIS, and you got brought into what looks like a Google Map-based system. For this case, we drop the pin at a given location close to Des Moines. And you can see that there is the hydrologic context. So it draws the basin boundaries. It gives you the information about different stream gauges within the basin, whether they are USGS or IFC bridge sensors, information about rain gauges, soil moisture probes, all of that at your fingertip. If you hover over a given site, you are able to pull up all the information. As I said, this is not an activity that we have been doing in a vacuum, but it takes a lot of partnership with many local and federal and state agencies. And here is just an overview of some of them. And the collaboration has been very fruitful across the board. And I think we complement nicely some of the other activities that are going on. So I'm just going to take a few minutes to give you an overview of where we are in terms of examination of climate change in the context of flooding for the state of Iowa. These are outcomes from a recently awarded project by through the Iowa Department of Transportation. Some of the work we did in the past was looking at detecting changes in the frequency of flooding, for instance, across the central US. And what you see here is an indication that across Iowa and many other areas of the Midwest, there has been an increasing trend in the frequency of flood events. You can see this darker red color indicates a statistically significant increase in trends in the number of flood events we have been experiencing over the past 50 plus years. This is consistent across the different seasons, and it's consistent across the level of flooding you are dealing with. As you go from left to right, you go from bigger events to smaller events. So from less frequent to more common events, but the picture doesn't change. It points to this increasing frequency in flood events. And there is a whole other story that explains these results in the context of climate change. What we've been doing is collaborating with colleagues at NCAR, the National Center for Atmospheric Research. And we've been using a data set that they put together, which is 13 years of high resolution simulations, for which they've taken ERA interim, which is a reanalysis product at about 0.7 degree resolution, so roughly 70 kilometers, and it has been downscaled using an atmospheric model. For those of you familiar with it, is the WRF model, the Weather Research and Forecasting model. And so the first step for us was to evaluate whether these control experiments, whether the data, the historical past that they generated was fit for purpose from a hydrologic perspective. And the answer was yes. And then we looked at what's called a pseudo global warming experiment, in which we assume that the current climate and weather reoccurs under future climate conditions. So using the RCP 8.5, which is the business as usual scenario under CMIP 5, what you do, you look at the difference between the future and the past, and you superimpose this difference onto the present time. Effectively is looking at the weather and climate in the today under boundary conditions that are coming from the future. And we use the Iowa Flood Center flood model to get a sense for what this would look like in the from a hydrologic perspective. And the answer is a little bit worrisome, I would say. What you see here on the top panel is the results for flood peaks. In the bottom panel are the results for volume, this volume discharge volume. A value of 1, which is this horizontal line, it's telling you that in the future, the conditions are going to be the same as today from a hydrologic perspective. Anything larger than, it means that you're going to have bigger flood peaks or bigger volume. For instance, a value of 2, it means that in the future, the same kind of systems, but with different boundary conditions, will give you twice as large of a flood peak. And you can see that there are these seasonal variabilities. You go from January to December, with the largest signal of change of enhancement of flood peak and flood volume and discharge volume occur in the late winter, early spring. And if you look at what the reason is that this is tied to the transition from snow to rainfall and also increases in precipitation in the spring, which are expected to lead up to a doubling in flood peaks and 1.5 times more rainfall volume. So with this, I'll stop, and I want to thank you for the attention, and I'll be happy to take questions whenever is the right time.
Perfect. Thank you, Dr. Gabriel. That was very informative and interesting. So, so now I will introduce our second speaker, David Heyman. David is a surface water hydrologist with the USGS Central Midwest Water Science Center. He has conducted a variety of studies during his 34-year and counting career with the USGS, including those focusing on flood inundation mapping, hydrological modeling, flood frequency and analysis, and documentation of the 2015 and 2017 floods in Missouri. David, I will turn it over to you now. Hey, David.
Can you see the screen?
No.
Not yet?
Not yet.
All right. And
now we can see your screen, but not the.
There you go.
Yeah. Okay.
There you go. All right. Sorry about that.
Oh, no problem.
Well, thank you very much, and good afternoon, everyone. I am David Hyman. I'm a hydrologist with the USGS and the Central Midwest Water Science Center that includes Iowa, Illinois, and Missouri, and I'm in the Kansas City office. And I'm going to briefly discuss a couple of ongoing projects that I'm involved with here in Missouri that look at stream flow and precipitation-based flood warning and inundation mapping. So as a brief overview of the Water Science Center, there are 27 Water Science Centers throughout the U.S. And in each of them, we have two similar functions. One is for science or interpretive studies, and the other is to maintain data networks. And those include surface water networks, groundwater, water quality, and in our particular office, we also have a couple of sediment laboratories. And in terms of the science, we have 6 sections here within the Central Midwest Water Science Center, and I'm in the surface water hydraulics and modeling section, and rely heavily on that surface water data network as well. So to provide an overview, I'm going to be talking about the stream flow based or stream flow driven product that by which we generate a flood inundation map, and then a precipitation driven product by which we also generate this map product. The USGS operates over 8,000 stream gauges in the United States, and these are operated in cooperation with state, federal, local agencies. And these provide also kind of serve as in many cases, a point of the National Weather Service forecast points are co-located with those. They have over 8,000 forecast stations throughout the conterminous United States. Here within the confines of our Central Midwest Water Science Center, we maintain primarily surface water stations. 286 are located in Missouri, but we have over 200 in each of the other 2 states. But we also include, again, the groundwater monitors and the water quality monitoring stations. And all that information is served through the USGS National Water Information System website. Another means of obtaining information from any of those 8,000 plus stream gauge locations is by use of the Water Now application. So if you text or email to the waternow@usgs.gov, you text the station ID. There's an 8-digit station ID associated with each of those gauges, and it will immediately return the gauge height and discharge, again, for any of those stations. One of the primary products from the stream gauging station is going to be this rating table or stage discharge relation. that is useful in the products that I'll be talking about. So at the stream gauge, we continuously measure stage, and then periodically, this could vary from weekly to every 4 to 6 weeks, depending on the station and conditions. We measure discharge at these locations using a variety of techniques depending on the amount of discharge. And then we correlate the stage with discharge and create this rating table. And again, I'll be discussing this a bit more in the following sections. So with our USGS flood inundation mapping program, we have two primary objectives, and that is to partner with local communities and assist them in developing flood inundation map products, and then provide this information online to the public, along with the real-time streamflow information and the National Weather Service forecast. This is an image of the USGS flood inundation mapping application, and each green triangle indicates a flood inundation map library. And here within Missouri, we have libraries available in the Kansas City area and then over in the St. Louis area as well. And each one of these libraries was developed using similar techniques, standardized techniques within, that are used throughout the USGS. The first step in the development of this of a flood inundation mapping library is to work with a cooperating agency, state, federal, local agency, and determine a reach of interest. And then that's going to contain a USGS stream gauge and a National Weather Service forecast site as well. Then once that reach has been selected, we obtain the topography. Usually this is through LiDAR, light detection and ranging data, with which we develop a digital elevation model, and then we'll go in and supplement that information because the LiDAR normally won't contain the bathymetry information. We supplement that information with bathymetry and structures that we obtain using conventional survey techniques. And with that, we'll develop a one-dimensional or two-dimensional model with which to generate our water surface profiles. One of the key steps in the generation of that model is a calibration. And so that's where that stage discharge rating comes in. We'll use that to calibrate at that gauge location. So we'll calibrate water surface elevations to a range of conditions at that site. And then hopefully we have some high water marks that we will have obtained within that reach as well. So we can not only calibrate at a particular point, but also calibrate at multiple points throughout that reach of interest. So the product that we'll generate from the hydraulic model are water surface profiles, and typically these are generated at 1 foot stage increments, depending on the accuracy of the topography that we're using. And then we'll generate these for a range of conditions corresponding to the National Weather Service action stage, or near bankful, up to and exceeding the 0.2 annual exceedance probability, or a 500-year recurrence interval flow. And then with that, the water surface profile and the topography will develop this static map library. And then the FIM mapper then displays not only the map library, but then the real-time stream gauge information along with the National Weather Service forecasts into our flood inundation map utility. And with that utility, then it allows you to see what the inundation and water depth conditions will be over a variety of stages. The current stage may be at or near bankful, and then the National Weather Service forecast might show it 12 hours later. It might be several feet higher, so you could move the slider and see what the consequences of those conditions will be as well. the FIM mapper also is available as a mobile app, and so it's not only on your computer but mobile as well. One of the tabs in the flood inundation mapper shows the historical flooding, and that includes the top 10 annual peaks that have occurred at that particular station over the time period of record. And it'll show that over the backdrop of the National Weather Service different flood categories, the action stage in yellow and flood in orange, and moderate flooding in red, and then the major flooding in purple. And then also it will show the annual flood peaks as well. And so you can get some perspective as how the current peak or recent peaks compare to historical conditions. Another tab that is located on the flood inundation mapper provides information on services and data. And so each map library has a reference link to a report that documents how those maps were developed, and then also has a link to the inundation polygons and the depth grids that were created. Another link is to the water alert application, and that application provides for any stream gauge in that 8,000 plus stream gauge network. It provides information that can be used to get notification of a certain stage threshold. So you specify the stream gauge information, you specify whether you want to be notified by your mobile phone or by email, and then when that threshold has been exceeded, whether you want to be notified hourly or daily updates, and then provide a stage of interest, whether that corresponds to a bankfull stage or whatever stage might be of interest to you. And then it will automatically send that notification to you and raise that awareness when those conditions have been met. I wanted to also mention that the National Weather Service also has a flood inundation mapper on their Advanced Hydrologic Prediction Service website. And in many cases, the USGS map libraries that are being displayed on USGS also are being displayed on the National Weather Service website as well, in order to get greater awareness. So what I've been talking about thus far are sites that are tied to those stream gauge or stream flow based flood inundation mapping that are tied to a National Weather Service forecast site. And these are generally going to be located in larger basins greater than about 100 square miles, with time to peak of greater than about 6 hours, because that's what corresponds to the National Weather Service hydrologic model. So, but in smaller basins and smaller communities, the National Weather Service product that they would rely on would be a flood watch or a flood warning, and these are issued at a sub-county area level that don't provide a lot of information then on terms of timing or magnitude or what the consequences might be. So that's where this next study comes in, the precipitation-based flood inundation mapping. Our first step is to locate a precipitation gauge in the basin of interest, and then we'll use precipitation information to feed into a hydrologic or a rainfall runoff model. What we've been using in our studies is the HEC HMS model. And then we also install a stream gauge in order to be able to calibrate that model and calibrate that rainfall runoff model and to the stream flow magnitude. Step 3 then is again to take that peak information or that hydrograph and develop a hydraulic model in order to develop a water surface profile and our inundation polygons and depth grids. And then step 4 is again to disseminate that information through our flood inundation mapper utility. So this is kind of another visualization of that process. We develop a precipitation matrix, develop hydrographs associated with those precipitation amounts, develop water surface profiles using the hydraulic model, and then convert that into a map library. One of the particular projects that I'm working on, we're also, the cooperator was also interested in knowing what the consequences are going to be of future land cover changes. And so what we did is generate a set of hydrographs for both conditions. And then we took that, so we take that same precipitation matrix, develop a set of hydrographs for both conditions, and then develop a map library from that. And then that way, the cooperator could be aware of not only what the volume changes are going to be, what the peak flow changes are going to be, but also what that might mean in terms of what that urbanization might mean in terms of greater areal extent of flooding and greater depth of flooding at key locations. The precipitation gauges that we use with this precipitation-driven mapping effort also can utilize that USGS water alert application. So again, you would take a precipitation gauge of interest and define how you want to receive that notification. And then in this case, you can define the duration and then the threshold amount. So if you're interested in an event of at least 3 inches over 2 hours, because that may correspond to a bankful conditions from the map library, then this will notify you when that is taking place and provide some advanced warning. Another product that is generated by the National Weather Service is a quantitative precipitation forecast, and that's available throughout the various regions in the United States. And depending on your location, it has different amounts of advanced notification. For our area, we have 6-hour increments or precipitation totals over 6-hour increments from 6 to 24 hours out, and we will develop a application that would allow us to, and the cooperator to receive notification when that precipitation is exceeded, when some threshold has been exceeded during any one of those 6-hour time increments. And that again will provide some additional advance notice, because we're talking about basins that are relatively small, so there is little advance notice in many cases. So anything we can do to extend that is a good thing. And with that, I'd like to thank you for your attention. And again, I also would welcome any questions after this session.
Perfect. Thank you very much, David. That was excellent. We really appreciate it.
All right, stop sharing.
Now I will introduce our last presenter, Dr. Sion Ham. Dr. Ham is currently an assistant professor at the University of Texas at Arlington. He finished his PhD in civil engineering from the University of Illinois at Urbana-Champaign. Before that, he worked in industries for 7 years as a researcher and a structural engineer on projects of more than 100 buildings and infrastructure design. His research expertise and interests with sensing infrastructure damage assessment includes rail structures, bridge structures, and nuclear power plants. Dr. Ham is also an expert in full-scale structural experiment testing and advanced numerical analysis, innovative sensitive techniques. Dr. Ham, I will turn it over to you now.
Okay, thank you so much, Dr. Rosa. This is, let me see.
Okay.
Okay, so are you able to see it?
Yeah, we can see your screen and we can hear you.
All right. Okay, welcome everybody. Thank you for your patience and thank you for your time for today. So let's talk about our topic presentation. So before we go through here, thank all our colleagues, the co-PI for Dr. No, Dr. So for collaboration for these projects. And also, especially I would like to acknowledge those my PhD students, extremely tremendous time effort for this project and then the other project as well. So thank you for all of them for effort for this one, okay? And then definitely after this presentation, you are welcome. Any question I would like to talk about that you answer for. Anyway, so this project's presentation is focused more like briefly here, how do we develop this system and how then I would like to share all this knowledge that we have some issue, how do we solve the problem that is also basically this is more like with technical I hope this is helpful for all of them for develop the not only just real-time water sensing and also as well as a lot of real-time inspection for pre-join other infrastructure. So this is a very simple structure here. This presentation will take probably 15 minutes for the finishing. So I think our team here mentioned about the flooding, that the flooding is a process safety hazard and emergency situation that maintain and also may cause also costly damage for transportation infrastructure and each operation. And not only just flood, particularly that flash flood is an issue for causing most flood related deaths and then also for a lot of $1 billion worth for economic damage here. So this is a very typical like urban damage in flooding that, as I mentioned here, that how do we kind of deeply looking here, and then especially I focus on today. I'll talk about more detail later, but we have what is our unique design and what is the special things that we can monitor. This is something new I'll introduce. So far, many years we have deployed those kind of water sensing system entire. There's all of the DFW area. We inspected the water level detection and then using this real-time renewable energy, solar energy that we use there, so we can provide some water level here. So that a lot of actually has now, but today is more we're not talking about today is how do we have results with the hydrogen model or analyzing. We're talking about really narrowed down and specifically one of the two sensors that we are really focused on the cost inexpensive code, the reliable non-contact system, and then also how do we develop and improve the dose system? What was the challenge? And then people has some face challenge that we try to do share some information to help for you all this develop some real-time monitoring system. And so especially today, so that's more like circuitry design and then computer design and how do we develop those things how do we improve it? So that is the main goal for today's presentation. So first, so having that goal, that we have three big main topic. One is we just narrowed down one or two nodes now. How do we focus on that? How do we extremely increase their resolution, like a 1 millimeter or 2 millimeter resolution water level at the same time, and then so minimize their cost, that less than $200 per unit cost, and of course that we also have some less maintained has that for data fee and etc. And of course we need a good quality of the extremely high resolution, but the really cost-effective one. The second one is also we have not only just we measure the stream water level or data, we also has a target for the different target of this payment water level, which is probably unlikely happening during the fall here. We also have some multi-target system that we can provide more information that hope those kind of idea or is to give more a better idea, or maybe you can use the data and idea. So yeah, last one is that keep it simple with the low cost unit, then you maybe have a lot of challenges that we have, that how do we save the energy, the extreme data? What about the 3-day consecutive 3-day raining and no sun day? How do we save the energy? Of course, you can increase battery life, and there's some better system here deployed, but how do we, let's keep a simple design. Now, how do we increase your extremely efficient the power saving plan? How do we design that? So I think I love to discuss so 3 topics here: cost effective and dual target and a dual MCU system. This is our main topic for objective, okay, for the presentation. So methodology. So first one is that this is pretty much straightforward, that we have 3 different areas: that's power supply, control system, sensing. And there are like we have a cellular module, and then we have a sensing system. We have a kind of minimize our customize the MCU microcontroller. How do we have a high resolution, 1 millimeter resolution of the water sensing, water level system, and how do we develop and stabilize the system? These are all the first step of effort that we deploy for many years. And so this is just an example that we have a lot of hope so once we have data flow for the algorithm of the UWLD, which is ultrasonic water level detection, our system, and then that one goes to the AWS system here to all the data sharing and then real-time monitoring. So that first one is we have this basic system we use that. So we have a couple of decisions here for the flow chart based on this flow chart there, so that you can minimize error that we have. We have some data provide reliable data with the temperature measurement, and then also we have data filtering here. So, for example, that this is one of the many people that study that there's the sound of speed sound is different than depending on the temperature. So we also use some calibrate our ultrasonic range that with the temperature measurement. So we have real-time measurement with the calibration, and also we have a lot of data filtering system, including machine learning system as well. But we are just using some median in this case. Just one thing I would point out that when it's very difficult. You can use a moving average. You should use like median or the other advanced machine learning system filtering for data, because when you use a moving average, that you maybe have unexpected data is boosting up your water level. So that's just basic things that I want to share. Of course, the last one is the real-time, and here we have AWS. So this AWS application is a lot of people already do this using this AWS cloud computing platform, that we just minimized our data structure, that extremely optimize, minimize our data, so that we have a faster react, and then also we have to save the data. There is data storage and then data transfer fee. That so we just want to minimize our effort is minimize those systems. The second is also very unique and important things that we provided today. The one of the challenges that we have, this is we propose the dual targeting on the each bridge here. One of the reasons that because 2 years ago the UTA student is drawn and died and accidentally in the high flash flood. That it was not that because the water is flowing over the bridge or low crossing bridge. This is more like we have anytime we have some train, there's a drain issue. That I have a couple of projects with the DOT, the stage project, that we have some drain system with the problem that, or infrastructure monitoring due to the many like a deterioration, and that caused by moisture and the chloride that all the bridge inspection. So not only just flood is impact that time, the casualty, and also we have a lot of a problem the infrastructure maintained after this event. So that we needed some monitoring that famous site as well. Of course, it's a very difficult to measure that case because, but there are many reasons that we just, it's maybe valuable research the idea. I would like to share that. So then also I'll show the result as well. And this is pretty much is the design is simple that we use some multiple sensor that here multiple target for the stream data and then payment side here. And then also the last one is we use a very simple customized microcontroller design with we keep it simple, like a less than very low cost effective device. Then how we can use, not we increase capacity of the battery, that how we can extreme. So we simply try to use a sleep mode with the COP process in the microcontroller. But also we have compared the other idea that we can use dual MCU, two microcontroller. How do we control the? Because we may think that our assumption was maybe the power saving time that we sleep mode, then maybe still have a lot of power consumption there. So we try to maybe minimize during the power saving mode case, then rather operating mode. Of course, there's a lot of we can improve those problems using the battery life and then or adaptive sampling or the other, etc. But how do we fundamentally we can improve this energy efficient way the system with a very minimized simple design that you can increase your power source, that you don't have any problem with the unit in here. That and then a lot of colleagues that might call it the real-time monitoring infrastructure, that there are a lot of issues that also this energy assumption, so that I try to help this to share this idea. So I think hold on a second, next page. So these are the design that we have a system representing that we are using the main MCU controlled by the another secondary MCU that is controlled by the relay and the MCU, that we maybe compared to the COP process, the slim mode, we maybe minimize the battery consumption for that one. Of course, this is the flow chart for algorithm that we are increasing our reliability that system. So so we can skip those here that we have customized both here. So let's look at this results first. So so we focus on the two neighbor bridge that we are controlling, the measuring the system here. So that one is in this area nearby here, that we have two sensors for each one. So we have 4 sensors to compare here nearby. And for the 6 months duration, we compare the data. Of course, we have some calibration for how we can accurately measure this water. Of course, the payment measuring is the most important, that extremely important challenge, that because you can see the clear color water, that how do we measure with the millimeter resolution that you increase the measuring. It's very difficult. And then of course, the good news is we don't have any good data of the flood, which is a good news. We don't have any flood issue in DFW this year. Hopefully it's not in the future, but we found some interesting results based on the payment measurement water level and the stream data as well. So here's another result that we compare with single MCU and dual MCU, that you can see that there's section A is the lack of the solar energy that here, that during the night or early morning, that if there have we give you a lot of reason we choose these two locations. There's a lot of challenges. There's many shaded area that we give you extremely case challenges there. So you can see that when you use dual MCU, you have a proper energy that you can increase, your charging energy, power during the section B area. While if you don't have any, even if you use a COP timer, that you still have some energy battery consumption problem. So the reason, because that when you use single MCU that we use, like I said, we use a COP present. That even if you have a power saving time, that you still have a lot of consumption during the power saving mode. So that we found a lot of this is a single time that you measure the battery consumption. Then if you measuring the 24-hour, that it's a lot of energy consumption that using the single MCU. While we use the double MCU, that we have clearly see the lower energy consumption here. That's why we have we can back up the signal here. So we compare with the NOAA's data here. There's Lake Arlington USGS here Arlington. There's water level measuring. So we compare with our sense stream data. This is the first is comparing the stream data with the lake. It's just slowly Lake Arlington water level is slowly increasing. We have two major events here, but there's it's clear correlation between our stream data and node 1, node 2 as well. And then you can see that slowly response because a large volume of the water lake here is a slow response, but is there good correlation. But it's not always that sometimes the water level is increased, but when you have the slope of the rainfall, that when you start rainfall, the slope is lower than you can see that there's no a lake water level is increased those time, and then if you have a slope is increased, then you still see some level, but it's sometimes we can see the strong correlation, but sometimes not here. So that's something we want to show the data. Of course, the two nodes, node 1, the two different location has a very similarity. Of course, that it's also depending on the drain issue or these there's a streams flows data that, but we see that a lot of strong correlation, of course, here. Sometimes we can see the little different here, but our correlation efficient, of course, is the same. But it doesn't have to be necessary to their similar correlation. Their correlation coefficient is high. It depends on the local condition in the stream data. One of interesting that we are finding from the pavement water level, we do not have any observation the increase that, of course, if you have more than 30 millimeter to 50 millimeter, that if it water level, that means it's a big problem in entire our Arlington City has a problem because the pavement has no any drain issue. Their problem drain system is a problem. That all the vehicle and you cannot go the drive there. That's very dangerous. It's very sensitive. So we can see that in this case that if you see all of the bridge, we found maybe higher wall level increase in each side of pavement. Each probably have a really significant problem. Although, but each one bridge node 1 shows some increase a little bit that the why is not, because it also has some drain issue. We find that we verify that. So this is just a kind of a good. We have some idea that we provide. So another things that we could want to talk about that there are a lot of research we can do. Some providing using this. Data that we can see the water level increase with the peak area or slope, or you can see there's some acceleration that with the rate of the water level. And you can see that right side one is the peak of the water level, and then of course we have area, which means how much the water is in during the short period of time that in the area of this water water data here, or slope as well. And this is the last slide that we can just provide. That we still have a lot of modeling, prediction modeling using some deep learning technology which is not showing up here. This is we just like I said, this is a very, very simple idea that we try to provide some technical idea, for including circuitry design and then an algorithm design for the high cost-effective, reliable data. But this is the one that I just want to give you a simple one. So There's one of the correlation between the value that normalized peak and that the value, when normally we have a normalized peak is higher than area, which is a very high chance of the flash flood. I mean, of course, we don't have any significant here, but if you have a very short period of time has a high slope, of course, that we can see there's some heavy raining sign here. So that is one of the things that we can just give a very simple one, the result here. So this is the conclusion. We have a very, I don't want to read all this in one, but simply, we have a new cost-effective, extremely lower price of the, but extremely high resolution of the 2 millimeter resolution of the water level system. Also, we deployed both pavement side and then the stream side as well. And then for sensitivity wise, of course, the pavement has measurement is extreme. Well, of course, we don't see any results that time only one time because they're draining issue. But if you have something for certain level of water increase level on the pavement, that may be a significant problem in the in the transportation area at event or after event as well. So of course, we have a dual MCU is also very effectively increase your energy consumption saving mode. So I hope this technology also can, a simple idea, can deploy in any other area, structural monitoring or any real-time monitoring as well. Okay, so thank you so much for today's presentation. I love to see so many comments and then questions. Thank you.
Thank you very much, Dr. Ham. We certainly appreciate that.
So let me make host for you.
Okay. Okay, so this concludes the presentation portion of our webinar. Now we will start receiving questions from the attendees. So please, if you have any question, please feel free to type it in the chat box. So I can see a question to Mr. David. So the question is, how do you measure the volume of discharge during floods? Do you use the same methods and equations to measure discharge to rivers under normal conditions, or are there special methods for measurement?
Okay. Yes, the basic technology that we use over the range of conditions is the acoustic Doppler meter. And so what is that's doing is sending out an acoustic pulse that tracks particles in the water and obtains the velocity from that. And then depending on what the conditions are, that determines the means by which that equipment is used. So for instance, if it was shallow water, less than a foot or two, you could use a acoustic Doppler meter attached to a wading rod and get discrete measurements. But the majority of measurements are going to be made with an acoustic Doppler current profiler that's attached to a tethered platform. And then the operator can walk across the bridge deck and tow that platform, and it's collecting information on velocity throughout the water column, and it's also tracking the bottom of the channel, so you're getting both velocity and cross-sectional area, and from that it'll compute a measurement. And so as long as the conditions allow someone to walk across the bridge, they can collect the information over a variety of conditions. And then if the bridge is impassable, then the operator can either use a small remote controlled boat or a full-size boat with an acoustic Doppler current profiler attached to it. And so they can just take the boat and go across the channel and obtain the discharge measurement that way as well. And if that peak is missed or the equipment fails, let's say the gauge is not in operation, then another method would be to conduct an indirect method, or at a location where a measurement wasn't possible. You you could obtain a discharge estimate from the indirect method by using the water surface profile through a contracted opening and then use equations to do that. But that's going to be probably plus or minus 25% accuracy, whereas with the acoustic Doppler current profiler, that's going to be more in the order of 5 to 8% accuracy. So basically the same techniques over a wide range of flows, but just a different means of deploying that technique.
Okay, great. Thanks, Mr. David. So I have a question for Mr. David too. It's related to the groundwater table. So actually my background is in the area of asphalt and pavements. So I remember in one project we were trying to evaluate the effect of the groundwater table on the performance of surface treatments. So one thing was a challenge in this project is to get the water levels in Louisiana. So do you have an idea if this data is in the USGS website? Because I remember I tried accessing this, having an access to this data, like the groundwater levels in Louisiana, and I'm not sure what is the latest data or the latest groundwater measurements that are available on the USGS website.
There should be data, real-time data available at many locations throughout the country. I can't speak in terms of Louisiana, but here in Missouri we have 150 stations measuring groundwater data. I'm guessing hourly, and that should be up to the current times. So, but again, with Louisiana, I'm not sure what might be available there. I'm guessing there is some there, and that it should be available through that National Water Information website.
Okay, and this data in Missouri, it's accessible to the public, right?
Correct.
Okay, perfect. So I can see a question to Dr. Gabriel. It's asking about whether the application that you presented, does it shows the inundation in pavements after flooding, or it just shows the inundation in rivers and lakes?
I missed the first part. So the inundation
in pavements, like if there is a flooding and after the flooding, specific pavements or roadways are inundated. So could the application determine the inundation or flooding levels for a specific pavement or highway after a specific flood?
Yeah, so these are in a sense static maps. So they have been computed and they've been developed based on best practices. They're not real-time maps, and so this is what we're currently working on now, is to have real-time flood inundation mapping that would be available for purposes the way you are describing. What you could do is, if you know what the water level is, you can go and see what the inundated areas would be. And one application that we've been examining is how to design, how to identify the best route to go from point A to point B, keeping in mind areas that may or may not be flooded. Does it answer the question?
Yeah, absolutely. Okay, so I think this concludes the Q&A, our Q&A session. So I do want to thank again the three presenters. I think this really turned out to be a very well technical program and presentation. Again, I want to thank the attendees. Please let me know if you have any questions about the webinar series and about TranSET. Otherwise, have a great rest of your day. Thank you.
Thank you very much. Bye.
Bye.
Thank you.
Thank you.
Thank you. Bye.